Hello to all the viewers. I am Ayushi Agarwal, Assistant Professor from Computer Science and Engineering Department of ABES Engineering College, Ghaziabad. Today, in this video, I will be discussing about IEEE Standard Floating Point Representation, which is a topic from Computer Organization and Architecture subject of Computer Science and Engineering. So, today in this video, I'll discuss about what is IEEE Standard Floating Point Number Representation, what are its types, and how to perform questions based on IEEE Standard Floating Point Number Representation. Now let us see what is IEEE Standard Floating Point Number Representation. So basically, this IEEE Standard Floating Point Number Representation is a type of a number system that are used to represent quantities. Now, what kind of quantities we represent by using this floating point number representation? Those quantities which cannot be represented by using integers due to two reasons. Either they contain the fractional values or they lie outside the range representable within the system bit width. Due to these two reasons, we are using floating point number representation to represent quantities. Now, this standard format of representing quantities which cannot be represented by integers is also stated as IEEE 754 standard. IEEE 754 standard of floating point number representation, which has been recognized, or you can say that it has been designed by IEEE Standard Association. So this particular association continuously works on designing various standards of representing different quantities, and one of those is 754 standard, which we are using today, or it is used in all different computer systems and various organizations for various calculations to represent quantities. So it has been established in 1985, but it was officially adopted in 1990 for various technical standards and various calculations. So a floating point number usually consists of floating point. Now, what do you mean by this floating point? Why we are stating this radix point as floating point? Let us understand this first now. In small classes, you must have read about decimal numbers. Now, what are decimal numbers? In basically, like when we have fraction values, for example, if I have 2 by 100 as my fraction value, if I want to represent it into its nearest value, I will obviously convert into its decimal form, which will be 0.02. Now, if I want its nearest value, if I round it off, obviously I'll got a value 0 after rounding it off. But for some calculation, this 2 by 100 must have some value. And now, while converting it to nearest decimal value, I'm having the value as 0. But this 2 by 100 must have some value. Then why there is a need for representing it to a 0? So there comes a floating point. Now this decimal point cannot moved or cannot be shifted from one place to another. But as soon as I can shift this radix point or decimal point from one point or from one position to another, at that point I reflect this radix point as floating point. So floating points are the radix points in decimal numbers which can be shifted from one position to another, and hence comes the another number system, that is floating point number system. So if I want to represent this value to in a form of floating point numbers, I can write it as 2 into 10 to the power minus 2. So this is equivalent to 2 by 100. So this 2 by 100 nowadays, any fractional values represented in a form of floating point numbers. You can have a few examples like the speed of light, or the age of the universe, or the speed of electrons. Everything is now represented in a form of floating point numbers. So there are various methods or various standards of representing floating point numbers, and among all those standards, we are studying this 754 standard. So in this 754 standard of floating point numbers, we represent any floating point number in a form of m into base to the power of exponent. So this is what it is represented over here. This 2 over here is our m. M stands for Mentesa. This 10 stands for base. We have abbreviated as capital B, and this -2 is our exponent. We can abbreviate it as small e, or we can abbreviate it as capital E. So this is our scientific notation for floating point numbers, m into base to the power of E. So m is the Mentesa, that is the integer value. Base is, in case of decimal number, we will have a base of 10. Whereas if we want to represent the same format in binary numbers, at that time this base value will convert to a 2. And this is our exponent, right? So this is our scientific notation for our floating point number representation. Now let's move on. Now, here I'm going to discuss you about what are the two types of IEEE standard floating point number representation. So we have two methods, or you can say we have two types of IEEE standard floating point number representation. One is single precision and another one is double precision. So now let us see both these two types one by one. Let me first summarize you points about single precision. Now in the single precision means any floating point number can be represented completely in 32 bits, right? And what will be the range of representation in computer system? Now the range will be 2 to the power minus 31 minus 1 to 2 to the power 31 minus 1. This is the range of the values which can be represented in floating point numbers by using single precision of IEEE standard, right? And here we have one equation of calculating a biased exponent. We represent biased exponent by E dash, which is equals to E plus 127. So in case of single precision, we have bias value of 127. We will see how we can calculate this. First, let us understand just the equation. Now, in further content, we'll be discussing about how to calculate this bias value, right? So these are the basic points about single precision. When we come about the double precision, in double precision, any floating point number is represented in 64 bits. And the range of representation with breadth in computer systems over here is 2 to the power minus 63 minus 1 to 2 to the power 63 minus 1. So this is the range of numbers that can be represented in double precision. And over here, biased exponent can be calculated as E dash equals to E plus 1023. So over here, this 1023 is the bias value for double precision, and in single precision, 127 is the bias value. Right? So these are the basic points for single precision and double precision. Now let us see what is the range of breadth for those components we have just seen in the previous slide. This is Mentesa, exponent and base over here. So while discussing about the single precision and double precision floating point number representation, if we have decimal numbers, so obviously our base will be of 10. And if we have exponent values, our base, binary values, our base will be of value 2, right? Now, let me make you understand about the Mentesa. Our M or Mentesa is the integer section of the values. So in case of 32 bits, or you can say single precision, our Mentesa will be of 23 bits. And in case of double precision, our Mentesa will be of 52 bits. Talking about the exponent or E, In case of single precision, our exponent will be of 8 bits. And talking about the double precision, our exponent should be of 11 bits. So these are the basic points about single precision and double precision in floating point IEEE standard representation. So you can just summarize, or you can just easily state this, that types of IEEE standard are of two. First is single precision, second is double precision. In case of single precision, the value or any value of a number can be represented in 32 bits, and in case of double precision, any value can be represented in 64 bits. The range of width in case of single precision is 2 to the power minus 31 minus 1 to the range of 2 to the power 31 minus 1, whereas in case of double precision, the value is 2 to the power minus 63 minus 1 to 2 to the power 63 minus 1. In case of single precision, the exponent equation is E dash equals to E plus 127, whereas in case of double precision, the exponent or bias exponent equation is E plus 1023. Now this 1027 is bias value in case of single precision, and 1023 is the bias value in case of double precision. Talking about the three basic contents of any floating point number representation in case of 754 standard, we have three basic formats, that as we have stated in previous slide, that m into base to the power of e, we represent this way. So in case of decimal numbers, b will be 10. In case of binary numbers, b will be 2. Talking about mantissa in single precision, the mantissa should be of 23 bits. In double precision, it should be of 52 bits. Talking about the exponent, in case of single precision, it should be 8 bits, and in case of double precision, it should be of 11 bits. So this is the basic difference between single precision and double precision. Let's move on and let's see what are the main components of any IEEE standard floating point number representation of 754 standard. So there are three basic components. First is the sign of the mantissa. That means our integer section is positive or negative. If we have decimal numbers, we put plus sign or negative sign representing the numbers as positive or negative. And if we have binary numbers, in that case, we put 1 for negative numbers and 0 for positive numbers. So this is a sign of the mantissa. Now talking about the biased or modified exponent, we have just seen in case of single precision, we have modified exponent e dash equals to e plus 127. And in case of 64 bits, we have seen e dash equals to e plus 1023. So this is our equation of modified exponent in case of 64 bits, and this is for our 32 bit. Now let us understand this third point, normalized mantissa. Now this normalized mantissa means while using your value in the form of decimal representation, floating point representation, your floating point or decimal point, or you can state it as radix point, must be situated or must be adjusted to such a state where just before the decimal point or the integer section of any floating point or decimal number must be either 1 or some value, but it should not be 0. It should not be 0. For example, if I have number as 1, 0, 2, 3, 4, so I must first normalize this value as 1.0234 into 10 to the power 1. So then I can use my value. That means just before the radix point or floating point or decimal point, I must have some value as 1, either 1 or some other value, but not 0. So that is why this is set as normalization of mantissa. Now in this case, I have mantissa value as this. That means the content or the values after the radix point are considered as mantissa while converting any floating point number representation in the IEEE standard. right? So by default, either the value before the radix point must be 1 or some other value, but not 0. That is stated as our normalized Mantissa. I hope these three terms are now clear. Now let's move on how to convert or calculate or represent any number in 32 bits or in 64 bits. Now let us see one by one. First of all, let's see this example. I have taken a value as 1460.124 to the base of 10. That means this is our decimal number, and its equivalent binary number is this. So now let us understand the steps. Whenever you are provided with some decimal value for representing an IEEE standard, first step is convert that decimal value to its equivalent binary value. I have already converted it over here, but whenever you get the value, first convert the given decimal value to its equivalent binary number. So your first step is convert your given decimal value to binary value, equivalent binary value, right? So first step is this. Now second step is normalization. Normalization of what? Normalization of our Mantissa. So first normalize your Mantissa and then continue with further calculations. So normalization of Mantissa, just I have explained you that your decimal point or your radix point or your floating point must be situated at that state or that position where just before the radix point there should be either value 1 or it should be some other value. So now you can see that just before this radix point, I have so many values. And just now I have stated I should have either 1 or any other value. That means single value. So we will shift this our radix point to the position over here. And we have normalized Mantissa as 1.0, 110, 110, 1000001 into we have shifted how many positions? 1 2 3 4 5 6 7 8 9 and 10. So we have since we are using binary value, so our base value will be 2 and we have shifted positions 10 towards left. So we will have exponent value as 10. So this is our normalized Mantissa step in case of converting any binary number in the form of IEEE standard of 32 bits. So now over here, we have our Mantissa value as this, we have exponent value as 10, and we have base value as 2. This is the correct format for IEEE standard. Further, let's move on. This is our second step now. Now our third step is calculating the exponent value, that is E dash, or you can say that modified exponent value E plus 10. So not 10. In say first precision, it should be 127. Okay, now let's calculate this equation. We have small e value as 10. This is our small e. So now let's calculate modified exponent value. Over here, it will be 10 plus 127, which will be equals to 137 to the base 10. Now what I will do, I will first convert this 137 to its equivalent binary number. So its equivalent binary number, you know how to calculate the binary value for any decimal value. So when you convert this 137, you will have the value as 1000, 1001 as its equivalent binary number. So this is the equivalent binary value for 137. So this is our exponent value. And since our value is positive, so my sign value is equals to 1. My Mantissa is equals to 0110. 110, 1000001, and my exponent or E value is 10001. Now let me show you how to represent a given number in 32 bits. Let's draw our structure for representation. This is our sign bit. Next comes our exponent section, and last comes our Mantissa section. So this is our Mantissa. In 32 bits, we must have 23 bits for our Mantissa. Then our exponent of 8 bits and sign bit. Okay, so this is our 23 bits of Mantissa. Let's put our Mantissa over here. 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1. Our exponent value is 1, 0, 0, 0, 1, 0, 0, 1. Okay, and our sign bit value is obviously, since our value is 1460 is positive, so we will put sign value as 0. So this is our representation in 32 bits. Now let us check. Our exponent must be of 8 bits as we have stated earlier. Now count the number of bits: 1, 2, 3, 4, 5, 6, 7, 8. So we need not to modify our exponent further. We just keep this value as it is. But in case if we do not get the value that is fulfilling our bit length of 8-bit, we will put extra zeros on right hand side. Now let us see in case of Mantissa. Our Mantissa should be of 23 bits, but see over here we do not have complete 23-bit Mantissa. Let us count the number of bits: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we have 13 bit of Mantissa, but according to the rule it should be of 23 bits. So how we can convert this or modify this value to 23 bits? We will put extra number of zeros towards the right. So we will put how many zeros? 10 zeros. So after adding 10 zeros to this Mantissa, our complete Mantissa will be of 23 bits. Now let's put 10 zeros over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 13 over here, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So now this particular complete value is our complete Mantissa. And this is how we can represent into 1460.125, a decimal value, to its equivalent binary value in IEEE standard. So first step is convert the given decimal number to its equivalent binary number. Then second step is you need to normalize the Mantissa, means before the radix point you must have either value 1 by default in case of binary numbers, whereas in case of decimal numbers either you must have value 1 or some other value, but irrespective of 0. It should not be 0. Next step is you should calculate the biased exponent by calculating, in case of single precision, E dash equals to E plus 127. So you will have the value of E over here as 10. You might have other values also in case of other numbers. So just add that value to 127. Whatever value you will receive, convert that value to its equivalent binary value, and hence you will have the value of exponents. Now, in case of single precision, your sign bit must be of 1 bit, that is 0 over here, since our number is positive. Your exponent should be of 8 bits. So in case of single precision, it is fixed of 8 bits. Now over here, our exponent is already coming of 8 bits. So we will not modify it any further value. In case of Mantissa, it should be of 23 bits. So we will have our Mantissa over here. We have just find it out our Mantissa. So now our Mantissa is of 13 bits. So we will convert it or modify it to 23 bits. So how we can modify? Just add the number of zeros that will convert the given value to 23 bits. So this is how you can convert any decimal value to its equivalent binary value in IEEE standard format of single precision. Now let's move on and see how we can convert the same value in double precision. So in case of double precision, first we should know that it should be of 64 bits, right? Again, we will follow the same steps. First, we will convert the given decimal number to its equivalent binary number. This is our equivalent binary number. Now, what you will do, you will normalize the value. So when we normalize it, we will again have the same value at 1.0, 110, into, since it is our binary value, so base will be 2 and 2 to the power 10. So this will be a normalized value. So from here we have Mentesa value as 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1. This we have calculated our Mentesa. Next, we should know our sign value. So our sign value, since our value is positive, so sign value will be 0. Now let us calculate our exponent. So bias exponent E dash equals to E plus 1023. So over here E value is 10. So it's 10 plus 1023, which is equals to 1033. Right? This is our decimal value. Now we will convert it to its equivalent binary value, which is equals to, you will calculate it as 100 0 0 0 0 0 1 0 0 1. So this will be our equivalent binary value for 10333. So now let us represent our this decimal value to its equivalent double precision standard. So first we will have a sign bit as 0, then we will have our exponent, and then we will have our Mentesa. Now, in case of double precision, it should be of 52 bits from 0 to 51. Now, from this 52 to 62, we will have 11 bits, and our last bit will be of sign bit. So, this is our exponent of 11 bits. Then we will have our Mentesa of 52 bits. So now just let's represent our answer over here. So sign bit, we have 0, and it is very easy to identify. Now we have our exponent. Our exponent value is 1000, 0, 0, 0, 1001. It should be of 11 bits. Now you can see that it is already of 11 bits. So we will not modify it, but if we do not get the exponent value as 11 bits, we will put extra number of zeros over here to modify it to correct 11-bit exponent. Since it is already of 11-bit, we will not modify it. Now let us see with Mentesa. Our Mentesa is of same value as we are getting in case of single precision. So we know that this is of 13 bits. So we will add that number of zeros that will convert it to 52-bit of Mentesa. So first let me write over Mentesa over here. So it's 0110, 1101, 00001. Now this is of 13-bit. Now I will put that much number of zeros that will convert this or modify this particular Mentesa value to how much bits? 52 bits. So we will add how many zeros? So let me get it to you. We have 13-bit over here. So let's convert it to 52 bits. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52. Now, this is the complete Mentesa over here in case of double precision. So from this, you can understand that in case of double precision, there is a huge range of number that can be represented, right? Since we are getting our Mentesa and we have added so many number of zeros to get the correct Mentesa of 52 bits. So from this, you can understand that this double precision is a very huge length of numbers which can be represented in this IEEE standard of double precision of floating point numbers. So this is our complete answer if we are representing any double precision format of IEEE standard for representing any decimal value. Let me summarize the steps. First of all, you will have your decimal value. First, convert this decimal value to its equivalent binary value. Then, second step, normalize your binary value to have a normalized Mentesa. So from there, you will get the normalized mantissa. Remember, in case of normalizing mantissa, before the radix point or floating point number, that means your integer section must have value either 1 by default, or it should have some other value in case of decimal numbers, but it should not be 0. So in case of binary numbers, by default, before the radix point, it should be 1, not 0. If it is coming 0, you need to shift your decimal point to such position where you do not have 0 just before or in the integer section of your decimal number. Then you will calculate your mantissa. You will get your normalized value of mantissa from your normalized value. Then calculate biased exponent. In case of double precision, your biased exponent will be of e plus 1023. Calculate the bias exponent, convert it to its equivalent binary value, and then you should know that how many bits are needed to represent sign bit, exponent, and mantissa, as these are the three main components of any IEEE 754 standard of floating point number representation. So this is how we can do single precision, double precision, IEEE standard 754 floating point number representation. So these are my references. I have used references from Computer Organization and Architecture of SHOM series and various other sites as well, from where you can get this information that how we can calculate and how we can represent a single precision and double precision. So thank you very much. I hope this whole content will be beneficial for you all to understand. Further, you can do some other values also by for understanding this single precision and double precision representation of IEEE standard. So thank you very much and have a good day.